Hello.
Hi, everyone.
Thanks for inviting us to this conference. It's great to be here.
The problem to optimize. This is going to be a supervised learning problem. So that means that we are going to use MNIST, the handwritten character digit database, where all of these images have their own label, and the label is the number. So the label would be 0. And the goal is to learn the mapping of labels to images. And I'm sure most of the people who are here have dealt with this data set before. It's very popular.
So when we started working with GANs, it didn't work that great. You can see some of the MNIST digits were pretty good, but images of faces or natural images like CFAR were not that great. But the good news is that about a year later, other researchers started exploring different ways of training the GANs and starting to have quite impressive success.
Well, the transition to not just one cognitive object, but many, so distributed intelligence, essentially, and how essentially this distributed cognitive form can internalize through time conditions and regularities from the environment into its own structure in order to achieve increasing complexity. What cognition would be in that sense is to make the improbable, make it become probable for the sake of preserving your pattern, as I mentioned before. And cognition would be in that sense how the way you pass information through your network of single units in order to make this learning happen. So this enables you to make this kind of prediction about your environment in order to preserve this pattern, simply much better than just having some of the entities die, just pass information. So change the entities, change properties in the entities.
In this autonomous vehicle, it's driving around the streets of, I'm here out on the West Coast this morning. It's out here on a sunny day, and it's recognizing objects as it's moving through the domain. And when I say recognizing, what it's really doing is it's using its image processing. For example, if we see here on the chart, we see something like a stop sign. It recognizes stop sign by looking at samples, images, and trying to infer what the image is. So in this case, we recognize something as a stop sign, and then we use the features of that stop sign, the individual pixels and the secondary elements, things like the shapes of the sign, to tell us something about what that sign is.
So this is our dashboard here. So you can see, so we have a search bar, and then we have multiple tabs. So this is the tool that we offer brands, and we offer searches along these 3 dimensions. So you can search for brands. So let's say I search for brands, let's say Starbucks, and I search for that. So some of these images could be NSFW, forgive me, because we do filter it out, but it's not always 100% sure. But, oh, okay, so thankfully none of the, so here's an interesting one. So here you can see that, there's an image of a dog drinking from a Starbucks cup. So we would put a box around the Starbucks, the pet mammal. So we found these contextual tags for these images. So we can loop through, oh, there's a Starbucks there. So, and there's a sports car. So our goal is to weight this engagement more by the potential popularity or our estimated popularity based on that. Takeaway number 1. Popular content, again, because I didn't show you a lot more detail than into that, but the popular content is sort of like music. If you think about it, like the Geico ads, and anyone who lives in North America would have seen this hundreds of times. So popular content is almost like music. That is, it has both repetitive and novel elements.
I'm going to give a high-level idea on how we solve this problem. So say this is the handset. Typically, when you download content, your handset sends a download request to an origin server or to a set of origin servers, which send the content back to your phone. We have added another level of servers in between the origin server and the handset. We call these accelerator servers.
After we build this co-crest matrix, we applied SVD, right? But why do we apply SVD? Because we don't want to use huge co-occurrence matrix like 1 million by 1 million matrix, which is also very sparse. And we want to reduce the dimension of that matrix without losing too much information. So for example, here is 2D graph, 2D data. And if you want to reduce the dimension of this 2D graph into 1, what would you do? So let's talk about evaluation. How we are going to test these word embeddings. Word2Vec is an unsupervised test, so there's no best way to objectively evaluate your output unless you define the object. So evaluation depends on your end application, but there is one way to evaluate embedding, and that is to test the analogy.
Let's look at some interesting, meaningful directions. So what we have here, we took a screenshot of when we looked for word book. So the word book is here in the middle, it's highlighted in red, and we isolated its top 100 nearest neighbors. Okay, so you have this collection of words that are the closest ones to book. But we are projecting those in this directional vector, if you will, from old on the left to new on the right.
By researchers, including Ian Goodfellow and collaborators, have shown that deep learning systems are very easily fooled. In this figure, you can see on the left-hand side columns are the original images, and the middle columns are the magnified adversarial perturbations. These perturbations are specifically crafted by the attacker to fool the learning system. And they are very small. Normally, they are so small that you can even see them by human eyes. And here they are magnified so you can see it. In this domain, the community has been trying to develop new neural architectures to learn programs such as sorting, addition, and so on. And there has been a long string of work in this domain for developing new neural architectures for learning different types of programs, such as neural Turing machines and neural programming interpreter, which won the Best Paper Awards in last year's ICRR.
So certainly some of us here will have some memory of that moment where we all talked about the idea of bringing your own device to work. And we shouldn't forget that there was a moment in time where if you brought this little baby to work and you started to retrieve the company email, you would be called in for a chat as in, are you out of your mind? As in, did you take PricewaterhouseCoopers emails onto your personal device? This is your first warning. 2 warnings and you're out. Today, we barely talk about it. As in, I just assume that any one of our guys will have company email, Slack, Google Drive, GitHub, Clubhouse, what have you, on all of their personal devices. And right now that our source code is being loaded onto some laptop somewhere in Manhattan that I'm not aware of. But that became normal.
As this arrives, we will get out of this period of super low GDP growth that we've been in worldwide, or at least in the developed world, and see a period of some number of years through this transition where we have absolutely massive GDP growth on a scale that no one's quite ready for. Now, the downside of that is that I think it will tend to concentrate in a small number of people. And this is part of the reason that we started OpenAI, is to make sure that this doesn't happen.
Inside of this, we've got a data directory. And inside of this data directory, as you can see, I've got a train and a validation folder. Now, if I go into the training folder, you can see that I've got a 0 and 1 folder. Now, if I go into the 0 folder and tell you what's inside, you can see that there are a bunch of cat photos. But in 1, there are a bunch of cat photos, or dog photos. And so there's the same data structure in the validation directory. It's just that the training folder is used for training images and the validation folder is used for testing images. And so we've got also, the 0 for cats and 1 for dogs inside of the validation folder as well. basically, this is just trial and error, all right? We start off with some sort of simple architecture, and what I do is I then, start stacking more and more layers on top of each other. I start experimenting with each layer, changing all the parameters. Like, for example, if we're not reaching enough test accuracy, but we're getting a lot of training accuracy, I know that, hey, it's probably a problem with overfitting, and then I do things like dropout, or I reduce the complexity of the model, or if it's just not increasing the accuracy, either it's too less data, or it's not complex enough.
You have an image, and you have a convolutional net. We use the ResNet, which gives you a representation, a low-dimensional representation, and you want to predict and to align this representation with all the words that are associated to this representation. So how do you do this? What we'll do is this. We just sample one word from this full list of words, and you'll say, okay, the ground truth is this word. This is the ground truth, and this is what you want to predict.
The first example that we looked at is basically in this case, we're looking at it's a two-sided conversation. So there's a customer and an agent speaking here. And if we don't record it and process it as stereo, it can be a little hard to read. So the first thing we're going to want to do is we're going to want to enable stereo. So in this case, once you do that, because there's two different channels, of course, then we can tell what's being said by whom, which makes this thing set already more actionable and more readable.
So here's an example. This is just a 2048-bit binary array, essentially. I've got 40 bits on. I can change this if I want to, but I'm going to keep it at 40 because that's 2%, and that's the typical sparsity of the brain. And the point I want to make here is that the amount of representations that you can show in this space is astronomically large. There are more ways that you can put 40 bits in this space than there are atoms in the known universe. If I'm a neuron, I have all these connections to other neurons. They might be proximal connections, which are feed-forward inputs from some space, or they could be distal connections, which are looking at other neurons like neighbors nearby. Each one of these is an SDR. So a neuron's view of the other neurons that it sees is an SDR. And at any point in time, generally 2% of them are on. Those all mean something. So the neurons it's connected to are telling it something about the current state of whatever's being observed at the time.
So basically, let's say, what is a probabilistic topic model? A probabilistic topic model is a generative model of a document. So let's imagine for a minute that you observe basically different topics. These topics you can imagine as being distributions of a word. So let's say you have topic education, you have topic sports, you have topic politics. These topics will each put different weights on all the words in the vocabulary.
So a VGGNet basically is an 18-layer convolutional neural network, and basically the idea here is that the network is trained on ImageNet to do classification on those tags that you see. And as you can see, for example, the last layer there, which is basically the classification score, tells you if the input image is car, truck, airplane, ship, horse, and so on and so forth. And the input to the network is basically RGB vector representation of the image that you have. Remember that I mentioned that Etsy items or listings basically have a set of text description and tags, and then they had images. So we have both modalities. We have the text modality, and then we have the image modality. So what we do is essentially just feed in the whole listing into our multimodal embedder, basically, which is essentially just extracting the image vector and then extracting a text vector, and then basically concatenate them together as one single multimodal vector representation of the listing.
Take a bare minimum outline and fill in the details. You can take photos of people and add random facial features. Take some foreign words, create them in your own language. Swap out objects in an image, like a horse for a zebra, or apples with oranges. Hey, now you can actually compare apples to oranges.
let's look at a demo. It's more easy to understand. So here we have a handbag. We try to draw a different shape. Like here in the right, we show images generated by the GAN, by the GAN model. And then when we click play, we will generate something that close to the GAN, but also have the original texture. That's what we are doing. And here another example, we can have shoes. And we can warp the shoe a little bit using a warping tool, and we get a shoe, thinner shoes. And then we can apply the same deformation to the input images. The most interesting app is from created by the Chris. He actually created a model from the edge map to cat. So you can draw a cat, and at left, and after you press process, it will create a cat for you. So you can draw random stuff like a bread, and you can create a kind of cat bread for you. So it's the more interesting. These are all the created by the artists and the users.
So in this graph, I'm showing you what happens if we take a neural net and apply it to an image of a car. If you look on the left, there's another one of these animation images that's meant to be read left to right, top to bottom. Toward the middle row, you can see there's the white car on a red background that we saw in one of the earlier slides. Anywhere left or above of that image, we've subtracted off an adversarial perturbation. And anywhere to the right or below that image, we've added an adversarial perturbation. We can also make maps of input space where we actually see the boundaries between the different classes. In this image, I show you a grid with several different maps of input space surrounding different test examples. Every little panel in this grid represents a different test set example from the CFAR 10 data set. And on the left, I show you a little legend for this map. The FGSM direction is a particular kind of adversarial example direction that we can look in.
Let's talk about random indexing. This is really, I really like this model. It's a locally sensitive hashing method. So it actually approximates the distance between the 2 points in the original target by context matrix. And there's this Johnson-Lindenstrauss lemma that says that if you multiply a matrix A by a random matrix MK, you will actually end up having a matrix BK where the Euclidean distance is preserved up to a specific epsilon. So the proportions of the distances will be exactly the same.
It's definitely been a pleasure. I thank the folks at the conference AIWTB for inviting me and for getting this set up. And I look forward to any conversations that you want to have offline. Thanks again. It was great having the chance to talk to you today. Cheers.
Thank you, everyone. And bye-bye.
Thanks. Over and out.
Thank everyone for joining in today. I really do hope this was able to help you out. And all right then. So thank you very much. That's going to be all for this this session today.
Thank you very much, guys. Cheers.